Hello. Welcome to today's lesson on radioactivity. Today we'll begin by exploring the heart of the atom, the nucleus. We will also understand how the nucleus becomes unstable. This will allow us to introduce the concept of radioactive decay, which enables atoms to achieve stability in their nuclei. Let's get started! At the heart of an atom lies its nucleus, composed of protons and neutrons. Protons are positively charged particles, while neutrons have no charge. You might remember that, charges repel each other, which means the positively charged protons within the nucleus are constantly pushing away from one another. This repulsion is quite strong, and without some counteracting force, it would cause the nucleus to fly apart. So what keeps these protons tightly packed together? The answer lies in a powerful force known as the strong nuclear force. This force acts like an incredibly strong glue that binds protons and neutrons together, but it only works over very short distances, within the tiny confines of the nucleus. The strong nuclear force is much stronger than the repulsive force between protons, which is why most nuclei remain stable. In many atoms, this balance between the strong nuclear force and the repulsion between protons is perfectly maintained, resulting in a stable nucleus. However, in some atoms, this delicate balance can be disrupted. This typically happens when a nucleus contains too many protons or neutrons, or when it possesses excess energy. Imagine the nucleus as a game of tug-of-war. In a stable atom, the teams are evenly matched, with the strong nuclear force keeping everything in check. But if one side suddenly gains too many players, too many protons for instance, the balance is thrown off. This imbalance leads to instability in the nucleus, which can cause the atom to undergo changes such as radioactive decay in an effort to regain stability. When a nucleus becomes unstable due to an imbalance, such as having too many protons, neutrons, or excess energy, it seeks to restore stability through a process known as radioactive decay. During this process, the nucleus releases energy in the form of radiation, which can manifest as different types of particles or rays. Specifically, the radiation can take the form of alpha particles, which are made up of 2 protons and 2 neutrons, beta particles, which are high-energy electrons or positrons, or gamma rays, which are powerful bursts of electromagnetic energy. The release of these particles or rays is what we commonly refer to as radiation. We will be exploring these kinds of decay in more detail over the next few lessons. As the nucleus emits this radiation, it often undergoes a transformation. This can result in the nucleus changing into a different element or a different isotope of the same element. A common example is uranium-238, a radioactive isotope that undergoes alpha decay to become thorium-234. In this process, uranium-238 releases an alpha particle, which is a helium nucleus reducing its atomic number from 92 to 90, becoming thorium-234, and mass number from 238 to 234.
In 1896, Henri Becquerel, a French physicist, embarked on an investigation into the properties of phosphorescent materials, those that glow after being exposed to light. I was particularly curious to see if these materials, especially uranium salts, could emit X-rays after being exposed to sunlight. To test this, I placed a piece of uranium salt on a photographic plate wrapped in black paper, expecting that sunlight would cause the uranium to phosphoresce and produce X-rays.
But something unexpected happened. Without exposure to sunlight, the photographic plate became fogged. This indicated that the uranium salt was emitting something entirely independent of the sunlight. Upon further exploration, I realized that the uranium itself was spontaneously emitting invisible rays. These rays were unlike any known form of energy at the time, and though I did not know it then, I had discovered what would come to be known as radioactivity.
I am Marie Curie, and the work of Henri Becquerel fascinated me from the moment I learned of it. His discovery of uranium's mysterious rays sparked my curiosity, and alongside my husband Pierre, I began investigating this phenomenon further. It was I who coined the term radioactivity to describe the spontaneous emission of energy from certain elements. Through our research, we found that the radiation emitted by uranium compounds was proportional to the amount of uranium present, proving that radioactivity was an intrinsic property of the atom, not a chemical reaction. This discovery led us to identify two new elements: polonium, named after my native Poland, and radium, which emitted radiation far more intensely than uranium. The impact of our work was profound. In 1903, I became the first woman to win a Nobel Prize, shared with Pierre and Henri Becquerel. Later, I received a second Nobel Prize in chemistry, making me the only person to win Nobel Prizes in two different scientific fields.
The discoveries of Henri Becquerel, Marie Curie, and Pierre Curie revolutionized science. They unveiled a new realm of atomic energy and laid the groundwork for numerous technological advancements, many of which have improved the lives of millions, and which we will explore throughout the remainder of this unit. Their contributions remind us of the power of curiosity-driven research and how it can lead to profound shifts in our understanding of the natural world. In today's lesson, we delved into the concept of radioactivity and understood why it occurs. We began by examining the atom's nucleus, composed of protons and neutrons, and the pivotal role of the strong nuclear force in maintaining stability. We then explored how an imbalance in the number of protons and neutrons, or an excess of energy, disrupts this balance, leading to an unstable nucleus. To regain stability, these nuclei release energy or particles, a phenomenon known as radioactive decay. In summary, radioactivity arises from the need of unstable nuclei to reach stability by shedding excess energy or particles. This fundamental understanding helps us grasp why certain elements emit radiation and undergo transformations to become more stable.